Okay, so our next talk will be by Abhishek Oswal, and he'll tell us about Tame topologies in complex and non-archimedean geometry.
Thank you so much for the introduction and the invitation to speak. It's a great pleasure to be here. I'm interested in number theory, and recently I've been interested in the applications of model theoretic tools in number theory. And so today I'm going to talk about Tame topologies in complex and non-Archimedean geometry. And so let me start by explaining the etymology of the phrase tame topology. So let me first also make an apology. I'm sorry to those who were also in yesterday's number theory seminar. A lot of the ideas from yesterday will also make an appearance today. But hopefully I'll indicate some potential applications, which would be something that I didn't discuss yesterday. Okay, so right, so let me start by explaining the etymology of the phrase tame topology. So the story starts with Grothendieck. So Grothendieck had this bold idea that the axioms of point set topology are far too general for the purposes of doing algebraic geometry. And he strongly believed that there should be a recasting of the foundations of topology, which would eliminate pathologies like the Cantor set and space-filling curves. And so he called this conjectural new version of topology as tame topology. And so here are some of the properties that one would like from such a framework. So one would like a well-behaved dimension theory. One would like finiteness properties, and objects in this framework should admit decompositions and stratifications into simple looking cells. And so tame topology is a broad term for any such framework that fits into this philosophy. And in recent years, a branch of model theory, namely the theory of o-minimal structures, is widely regarded as an instance of such a framework. So what is an o-minimal structure? An o-minimal structure is the following data. So for every non-negative number n, one is given a collection S sub n of subsets of Rn. And so these sets are called the definable sets of Rn. And so for each n, you're given a collection of subsets of Rn that you're allowed to play with. And these collections of sets should be closed under some basic first order operations. So for example, a definable set of Rn, if you take a definable set of Rn and a definable set of Rm, then the Cartesian product should be definable in Rn plus m. And each of these Sn's should be a Boolean algebra. So definable sets should be closed under taking finite unions, intersections, and complements. And thirdly, if you take a definable set in Rn and you project it down to Rn minus 1, you should also get a definable set. And finally, the minimality axiom requires that the definable sets of the one-dimensional real line should be simply finite unions of intervals. And by intervals, I mean simply connected subsets of the real line. And so whatever, so however complicated your sets might get in dimension n, they should satisfy the property that their projections down to the real line should still be simple looking. So they should be finite unions of intervals. And so this axiom imposes some sort of rigidity on o-minimal structures. And so two fundamental examples to keep in mind are the collections of semi-algebraic and semi-analytic sets. So for each n, let S sub n be the collection of all semi-algebraic subsets of Rn. So namely the Boolean combinations of all sets that are defined via inequalities between real polynomials. And similarly, one can start looking at subsets cut out by inequalities defined by real analytic functions. And of course, you can't take all analytic functions. For instance, the sine function has infinitely many discrete zeros. And so it would not be definable in any o-minimal structure. But it turns out that if you take a real analytic function and restrict to a compact subset of its domain, this is still going to be definable in some o-minimal structure, namely the structure of finitely subanalytic subsets of Rn. And so the power of o-minimal geometry comes from various algebraization results. And so so there's a classical result of Chow which says that every closed analytic subvariety of a complex projective variety is in fact an algebraic subvariety. And clearly this theorem is no longer true if the variety is not compact. So for instance, the graph of the complex exponential function is an analytic transcendental subset of C2. So this was an insight due to Peterson and Starchenko that instead of compactness, if one insists that your closed analytic subset is definable in some o-minimal structure, then you still recover Chow's theorem. So Peterson and Starchenko proved that any closed analytic subset of Cn, which is also definable in an o-minimal structure, is in fact algebraic. And so let me just sketch a recent proof of a result in Hodge, of a classical result in Hodge theory due to Baker, Klingler, and Zimmerman using o-minimal techniques to illustrate the power of the Peterson and Starchenko result. So let's start with a smooth projective family of smooth projective varieties. So for every point B in B, the fiber X sub B is a smooth complex projective variety. And so one can look at its singular cohomology, Hn X with Q coefficients. And this has the following structure. So if you tensor with C and compare this to de Rham cohomology, then Hn tensor C breaks up into HPQ. So the cohomology classes represented by PQ forms. And HPQ, the complex conjugate of HPQ is HQP. So this data here is a rational vector space whose complexification has such a decomposition is known as a Hodge structure. And so this is a fundamental object associated to complex varieties. And now given an algebraic subvariety Z inside one such fiber of codimension K, it naturally defines a cohomology class in the middle cohomology HKKXP, which is also rational. And so such cohomology classes are called Hodge classes. And so the Hodge conjecture states that all Hodge classes arise from such algebraic subvarieties. So let's get back to the family that we have. So given the smooth projective family X to B, one can define the Hodge locus of this family to be the set of points in the base, so the set of B and B, such that the dimension of the space of Hodge classes in the fiber at B is larger than typical. And so it's easy to see that the Hodge locus is in fact a countable union of complex analytic subvarieties. And moreover, if the Hodge conjecture is true, then when the set of Hodge classes is larger than typical, they should arise from algebraic cycles. And the set of algebraic cycles in a fiber at a particular point should be characterized by some sort of relative Hilbert scheme for this morphism X to B. And so with some additional argument, one can prove that the Hodge conjecture would also imply that the Hodge locus is in fact a countable union of algebraic subvarieties. And so this was indeed proved by Kathani, Deline, and Kaplan. So they show that Hodge loci are indeed algebraic. And more recently, Baker, Klingler, and Zimmerman have reproved this result via o-minimal methods. And so here's the main strategy of their proof. So one can study the variation of the Hodge structure in this family X to B via the so-called period map. So we have this map phi from B to a period domain, which is some sort of moduli of these Hodge structures. And their basic result is that you can put a definable structure on the period domain in such a way that makes all its special subvarieties definable. And with this natural definable structure, the period map, although a transcendental analytic map, has some tame geometry. Namely, it is also definable in an o-minimal structure. And furthermore, so the components of the Hodge locus in B are nothing but the pre-images of special subvarieties in the period domain. And so now by the first part, so since the period map is definable and since the special subvarieties are definable, one gets that the Hodge locus is in B is definable and complex analytic. And then applying the Petersel-Starchenko's result, they reprove Cattani, Deligne, and Kaplan's theorem. And so as is often done in number theory, one would like to treat both the Archimedean and non-Archimedean places at an equal footing. So it was a natural question to ask for non-Archimedean analogs of the o-minimal machinery. And so, over the p-adics, the role of the complex numbers is played by CP, which is the completion of the algebraic closure of QP. So CP as an abstract field is isomorphic to C, but its topology is vastly different. It's totally disconnected. And so it would be a bit surprising that there would exist some sort of an analytic geometry over CP. But there is a nice theory of analytic geometry over CP, namely Tate's theory of rigid analytic spaces. And much like real subanalytic geometry, one can study subanalytic sets in the p-adic setting. And so this has been developed by Denef, Van den Dries, and Lipschitz and Robinson. And then the analog of o-minimal structures have been studied by McPherson and Steinhorn. So they introduced the notion of C-minimal structures. And more recently, one can sort of slightly generalize C-minimal structures to what we call tame structures. And so in my thesis, I developed the notion of tame structures, developed some basic dimension theory of these tame structures. And we prove an analog of the Petersel-Starchenko's results. So if you have a reduced algebraic variety over CP, then a closed analytic subset of its rigid analytification, which is also definable in a tame structure, must in fact be algebraic. Right, and so so the hope with this result is that similar to the applications that o-minimality and Petersel and Starchenko's result has had in studying variations of Hodge structures and period maps, the hope is that this result, the non-Archimedean analog of Petersel and Starchenko's result, would help us better understand images of period maps in the p-adic setting and variations of Hodge structures in the p-adic setting. Yeah, thank you.
So in the p-adic case, what word can you use when you define something in this minimal sense?
Could you repeat the question again?
What is the language in which you may speak to define things in the p-adic case? Can you use the valuation?
Yes, absolutely. So, the more geometric way of thinking about it is, so it's a structure on CP again. So there are going to be subsets of CP to the n for every n. And the minimality axiom is that the definable sets of CP should be Boolean combinations of open or closed disks. So it's a classical result that semi-algebraic subsets of CP or even subanalytic subsets of CP look exactly like Boolean combinations of open and closed disks. So that's the minimality axiom that we impose. Does that answer your question?
Questions?
So in the analogy, when you were talking about o-minimal structures, you put a condition on what the definable subsets of R were, not what the definable subsets of C were. So could you comment about that?
Yeah, so in the real case, right, so for Chow's theorem, I mean, yeah, it's really special because the algebraic closure is of R is finite over R. So like but in QP, the p-adic and the CP settings vastly differ. So like there's a theory of p-adic subanalytic sets, which was around before the theory of CP subanalytic sets. But to go from QP subanalytic sets to CP subanalytic sets, it requires it's a lot more machinery. But yeah, so like in principle, one could restrict attention to talking about subanalytic subsets of QP to the N and work there. But for the purposes of this algebraization result, it's more natural to work over the algebraically closed field CP.
In the work of Bakker, Zimmerman et al. In the second paper, they heavily rely on work of Schmidt about unipotent vanishing cycle in the disk.
Yes.
Do you know, is there a p-adic analog of that in this rigid setting? Because that's a very important ingredient. They have not managed to, they don't shortcut that part. And that's also used, of course, in Deligne and Kaplan.
Absolutely.
So I'm asking in the p-adic so I'm just saying that somehow this o-minimality finishes the game off, you're sort of close and then it finishes it off brilliantly without somehow shortcuts is everything. But you do need to be in quite a well understood case before about the nature of the polarity.
Yeah, I'm not sure I know whether such an the analog of this of Schmidt's results hold in the p-adic setting. I'm not very familiar with this work. But maybe someone in the audience knows this. I don't know.
I don't.
Okay, let's thank the speaker again.